Prediction markets have been one of crypto's true success stories. In the recent presidential elections, they captured mainstream attention, and billions of dollars were positioned using blockchain technology. In this video, I'm going to show you how I built a simple binary prediction market using Stellar's Soroban smart contract platform. All the code that we're going to be using here today is open source on GitHub. There's links in the description, or you should be able to Google Soro Market GitHub and it should come up. So the way this works is we're setting up a market for a true or false outcome. So it could be something simple like James will be the next president of the USA, and people can bet true or false on that. That might seem ridiculous, but let's see what happens after another 3.5 years of Trump drama. If we jump into the code, we can go into contracts, source. We've got the main Soroban smart contract in lib.rs and a unit test suite in test.rs. I'm opening up these in VS Code just because they're a little bit easier to see. So to start off with, in the main contract, we're importing the Soroban SDK and the crate for interacting with tokens. So I'm going to be using set41 tokens to place kind of bets on whether the outcome is going to be true or false. This could be something like USDC. We then go on to define some data types, and this is probably the most interesting part of this contract. So we've got some enums here. An enum is simply a numerical way to order data. So in this example, we've got the state of the contract. So it's undecided when it's first set up. Then it's either true or false. And this is a very efficient way of ordering the data because it's setting it to 0, 1, 2. So the enum is basically a way to condense that data down to a numerical form, which is easier to store on chain. We then have a custom structure, which is set here for bets. And each bet is going to have an address for the user, an amount, whether they're betting on true or false, which is a Boolean, true or false, and another Boolean to say whether they've claimed it yet or not. Then we get down to the storage keys, and we're using storage keys here because it's an efficient way to create a map of the users and their bets. So we've got another enum, which is 0 for Oracle, token, true, total, false, total. And these are just kind of standard key value pairs almost. You're creating an address for the Oracle, a token contract address for whichever token you're going to use, the total amount bet on true, total amount bet on false, the market, which is a string, the state, which we've already looked at, is this outcome state. And then we're creating this dynamic mapping for the bets. So for each contract address that interacts with this contract, they'll have this assigned to a enum, which increases dynamically, and it's an efficient way to handle that amount of data. We can look that up later, so we can pass in the user's address and find out how much they've bet and whether they bet on true or false or not. Now let's go into the contract implementation, and we've got a few functions here. So the first function is a setup function. This would be called by whoever's setting up the market itself. They're going to define an Oracle address. This is a source of truth, bringing the real world data on chain. The token address, which is whatever stable coin or digital asset you want to use. Anything that's set41 should be compatible. And then you have a market, which is a string, which is just a text-based statement, which can be later updated to be true or false. So you could have something like, this smart contract will compile and pass all its units tests first time, and then we can put that on chain. This contract is set up as a single contract for a single market. You can't set up multiple markets in a single contract. It's a design choice, A, for simplicity, and B, because transaction costs are so low on Stellar, it means we don't have to be concerned about the efficiency of deploying multiple contracts and the cost within that. So if the market's already set up, we're just going to panic and revert the transaction. We'll then set in the storage for the Oracle, the token, the true total, false total, market, and the state, which is currently undecided, which actually means the market is live. And we're getting that from here. And the 0 factor, we're getting just setting an I2, 128 and 128-bit integer. The next function is a bet function. So once the market's set up, people can go and bet on this, either true or false. They're passing in their user's address, the amount they want to bet, and to bet whether it's true or false. We then set up a shortcut to the storage, which is persistent storage, and we can get the state and check that that's actually undecided, so the market's live. We can then check if the amount is greater than 0 and panic if it's not, and also check that the user hasn't already bet. So again, to keep this contract free of any bugs, we're only allowing 1 bet per user. In a production environment, you might want to change that so that users can kind of top up their bets on a single market. When using the token client from script 3, which is this crate here, and we are using that to transfer the tokens that the user has from their wallet to the contract address. Now they're going to need to call approve on that first, so they're going to need to approve the spend of the tokens before we can take them with using the contract. If they're betting on the outcome being true, we simply get the true total from storage, add on the amount they're betting, and then save that back to storage. Same for false. We then set up our custom structure for the bet itself. The user's address is here, the amount they're betting on, what they're betting on, true or false, and the claimed amount at the time they're placing this bet is false. And we're setting that to the storage keys bets user. So this is the dynamic array that we looked at earlier, or the dynamic mapping here. So by doing that, we can create a separate piece of data within the contract so that we can store individual users' bets individually, and we can take them out and change them without changing the whole amount of data which is stored for that bets mapping. It's an efficient way to create these dynamic key value pairs where you don't know how many keys there's going to be, you don't know how many users are going to interact with this contract. It's something I picked up off of Open Zeppelin's contracts. Their repository is also open source on GitHub, and you can learn a lot just by going through their code and seeing how you do certain things. The next function is a settle function, and this is just, we check the oracle is who they say they are, and the outcome they're putting through is either true or false. So we're setting a new state to true outcome or false outcome, and we're setting that to persistent storage here. Then finally, we have the claim function, and every individual user has to claim their own winnings. The reason we do it this way is if we try to settle all the bets with the Oracle transaction, we could kind of hit transaction limits for the computation on chain if there are enough users kind of bet on a single market, and that could cause a transaction to fail and all the funds to be stuck in the contract. So a much better way of doing it is to have individual users claim, and we know that the computation required for an individual claim can definitely go through. It prevents denial of service attacks and unwanted scaling issues. So for the claim function, we're checking the user is who they say they are, using require auth. This checks that the user is the invoker of the transaction. We'll then set up this store shortcut for persistent storage, and we're checking the state, and we're collecting the user's bet itself. And then we're checking they haven't already claimed the bet. We're doing this at the top to prevent re-entry. And we got the true total, false total, and the winnings is set to 0. We then got a scale variable, which is used to create a division of an integer. So if the user bet on true and the outcome is true, so if they're a winner basically, we have to work out their share of the total pot. We can't work this out as a decimal because integers don't have decimals. So we're going to scale it up to 1,000,000. So scale times the user bet amount divided by the true total. So their bet divided by the true total times 1,000,000. And then their winnings is their initial bet plus the false total, so the loser's pot, if you like, multiplied by their share, divided by that scale variable again. And then if they have won something, we set the user bet claim to true and set that to persistent storage before we make the transfer to avoid reentrancy. And then we've got the token address, and we're passing through a transfer. We're transferring a token from the current contract address, which is holding the funds, back to the user's wallet. Let's take a look at the unit test now. So if we go across to test.rs, and we're importing Soroban SDK and the test utils from the set41 token crate, and then we're we've got this helper to create a token contract, and we've got a setup function which is going to kind of set up. We're going to call this on every test to create an initial environment where the contract is set up and everything's ready to go. We're generating addresses for the Oracle and 2 bettors. And then we're creating a token contract. So this is just an arbitrary mock token. And then we're going to set up the client itself, which is basically deploying the Soroban smart contract for Soro Market. Then we're going to mock all auths. And what this means is in the contract itself, when we have this user.require auth, that will evaluate to true no matter what address calls it. We're creating an initial balance of 1,000 tokens, and then minting each bettor that amount and approving that the contract can take those funds. So we're approving the spend of funds, and we're basically giving permission within the token contract for the contract that we've deployed for Soroban Market to take the funds out of our wallet. So we can call a transaction in the Soroban Market contract, and that can then take funds from our wallet. It has approval or authorization to take those funds and deploy them to the Soroban smart contract, which will act as a holding wallet while the bets are in place. We're then calling the function to set up the market and returning all these values to the individual tests. So What that means we can do is in 2 lines of code for each test, we can set up a basic kind of boilerplate for us to use for testing different things. So the first test was just kind of checking store values, but then testing the totals and setting up some bets. We're checking some panic issues, making sure that if someone's already bet or the market's not live, then it panics as you'd expect. We then got some more functional unit tests where we're checking the claims, and before and after the user's claimed, the winner should have more than they've started with and the loser should have exactly the same amount. So this is after they've claimed, so they've already paid the premium to take out the bet. And then we finally got a multiple better simulation test to check that everyone's kind of getting paid out the right amount. Okay, let's try and run these unit tests. So I'm using Windows Subsystem for Linux for this. You'll need Rust installed and also the Stellar CLI. I'm going to run cargo test. A couple of depreciation warnings there for the register contract functions. There is a new function within the Soroban SDK which I haven't figured out yet. And there we go, 10 tests passed. Was it ever in doubt? Now let's go ahead and build it for WebAssembly. So I'm going to run cargo build target WebAssembly and set the flag to release. That's all finished, so now we can run Stellar contract deploy, set the target to WebAssembly file we just built, set the source to your account, and the network to testnet. That transaction is simulated, signed, distributed around the decentralized network, and finally we get this contract address. If we copy this, we can go into Stellar Expert, set the network to testnet, and check out our beautiful prediction market. I hope you've enjoyed this video. All the code that you've seen here is open source on GitHub, and there's a full tutorial and resources if you want to learn more about building Soroban smart contracts on the Stellar network. Thank you for watching.